Maximizing M3, pushing performance boundaries in a distributed metrics engine. I'm Christy Tan, and I'll be moderating today's webinar. We would like to welcome our presenter, Ryan Allen, Senior Software Engineer at Chronosphere. A few housekeeping items before we get started. During the webinar, you are not able to talk as an attendee. There is a Q&A box at the bottom of your screen. Please feel free to drop in your questions, and we'll get to as many as we can at the end. This is an official webinar of CNCF and as such is subject to the CNCF Code of Conduct. Please do not add anything to the chat or questions that would be in violation of that Code of Conduct. Basically, please be respectful of all your fellow participants and presenters. Please also note that the recording and slides will be posted later today to the CNCF webinars page at cncf.io/webinars. With that, I'll hand it over to Ryan to kick off today's presentation. Take it away.
Thank you. Hello, everyone. Thanks for attending. My name is Ryan, and I'll be walking through this presentation, Maximizing M3, Pushing Performance Boundaries in a Distributed Metrics Engine. And so kind of when we wrap up, we'll have 10 to 15 minutes of questions. We can read through the Q&A box and answer anything live that anyone might have on their minds. Cool. So let's begin. Just a quick background of who I am. So for the past year, I've been a senior software engineer at Chronosphere. At Chronosphere, we're a metrics monitoring platform company that fundamentally relies on kind of open source M3 as our core metrics storage. And so kind of over the past year, I've been working a lot on performance improvements to that system and just improving the scale at which it can operate. Prior to being at Chronosphere, I was working at a company called Applied Predictive Technologies. And so there, it was not really necessarily monitoring metrics, but it was time series related in that we were kind of building products that performed analytic aggregations on large financial transaction data sets. And so you can imagine, for example, kind of like a MasterCard transaction data set across many companies and doing various types of statistical analysis on that to understand spend behavior. So kind of the core thread there between my current role at Chronosphere and my previous role at APT has been related to time series in general. So just to go over kind of what is on the agenda in this presentation, first we'll just kind of talk about more abstractly what metrics monitoring even is, give some examples of some metrics in the series that comprise those metrics so we better understand what we're actually monitoring. The second piece is diving into the problems that come about in metrics monitoring, particularly when you reach certain scale. And then thirdly, we'll talk about how with the M3 project, we've sought to remedy a lot of these problems that we'll kind of enumerate throughout the presentation. Cool. So to kind of dive into that first piece, which is, what even is a metric, let's say. So kind of very abstractly and simply, one could think about a metric as kind of a generic schema for data that you would like to track and collect and aggregate over time. So a tangible example of this, for an actual engineer might be counting the number of HTTP requests. So, the name of this metric would be HTTP requests. This would be incrementing over time, kind of across all of your applications, let's say. And obviously kind of at that level of granularity, it's not that useful. Yes, you can understand kind of the total number of HTTP requests that are happening over time, but what you really care about are kind of the more granular characteristics about these HTTP requests, right? So that's where kind of metric dimensions come in. So every metric that you can conceptually think about actually can be broken out by various different dimensions, which describe in more granular detail the particular characteristics about that, instance of the metric. So a dimension, for example, with our HTTP request example could be endpoint. And so, one particular endpoint could be API/search, but then you can imagine many others that would be occurring kind of throughout a whole system. So you could kind of break out an HTTP request by the particular endpoint that it was associated with. And then furthermore, the same kind of another dimension that would be relevant for a HTTP request would be status code. So, 200 success, 500 error, et cetera, et cetera. And then it can even be kind of in more granular detail with dimensions that change over time very often, like something like git deploy version SHA. So, whenever a request is actually served by a particular server, the actual git SHA associated with the server serving that request is also kind of a piece of information that you could be attaching to this metric and caring about. So that's kind of more conceptually how you think about a metric and how like a user would approach metrics monitoring. But then if we think about what then under the hood a metric is comprised of, it actually all fundamentally boils down to distinct time series. And so if we look again just at our example of an HTTP request, kind of for every combination of all of the dimensions and their values, there is a unique kind of time series value that is changing over time associated with that unique combination. So if we just take this very kind of boiled down example, let's say we only cared about a few different dimensions, right? Endpoint and status code. Endpoint, we have 2 possible endpoints. Status code, we have 3. So for this request metric, while we conceptually think of it as one thing, when we're actually storing it and the way it's actually laid out on disk or in memory, it will actually be broken out into 6 total different time series. And if we were at, let's say, kind of another dimension that had 2 different values, that would then multiply that kind of total set of series again by 2. And so there's kind of this multiplicative inherent quality to metrics insofar as how they fundamentally end up being stored over time. So that kind of leads to one of the fundamental challenges surrounding metrics monitoring, and that is a challenge of scale. So again, because ultimately all these metrics are comprised of many, many different time series that we're storing in some location, we need to be able to kind of scale out our ability to store and then also retrieve all of these different series in an efficient way. And, over time, our environments have become, in a cloud native environment, one of having very ephemeral types of dimensions that would be attached to different metrics. So for example, within kind of a Kubernetes deployment infrastructure, a particular dimension that would be attached to nearly every metric would be the actual unique pod name associated with kind of the origination of that particular metric. And so, for example, let's say we had 3 different time series associated with a particular deployment, right? CPU, memory, and Go routines, all coming from the same single pod. If then we just redeployed, the same service with the same metrics, that would just double then the number of unique time series that we've generated kind of in that by just taking that deployment action. And so, as you can imagine, this is kind of like 3 different, series for just a single pod, but, across many different microservices, across, many different regions, et cetera, you can imagine how that easily can explode to millions and even billions of series that are comprising the metrics that you ultimately care about. So kind of in the kind of modern day solution architecture for metrics monitoring, there are a lot of really good options, but also, as we were describing, because of the scaling problem, it becomes more and more difficult to maintain this infrastructure over time because the solutions become more and more complex. So most people are familiar with Prometheus, which is a CNCF open source project. It's really kind of everyone's de facto go-to solution for getting out of the box metrics monitoring. So kind of in this first bucket, most companies when they're trying to adopt metrics monitoring as a standard, you just deploy a single instance of Prometheus. Everything just kind of works perfectly right out of the box, and all is well. Engineers can track their metrics over time. It's very easy to add metrics. It's all centralized in this one place for people to view them, and everything works really well at that kind of initial level of scale. But then over time, companies start producing more and more metrics. Engineers become more prolific in how they're instrumenting their applications, so they themselves are kind of leveraging the monitoring infrastructure to be able to be more granular. But that means more and more series ultimately are being produced under the hood that are being stored. And then you have again kind of systems like with Kubernetes, automated metrics that are being emitted and those tend to be very ephemeral, so they're constantly changing, thereby dramatically increasing the number of series being stored as well. And so then companies start running into challenges where you can continue to increase your Prometheus instance and just beefing it up, adding more memory to it, but eventually that becomes kind of like not a sustainable solution. So you have to come up with more interesting solutions. So often people will actually run multiple different Prometheus instances and kind of shard their infrastructure. So some subset of my applications go to Prometheus A, some different subset of my applications go to Prometheus B. And then in order to actually be able to, consolidate all of this data in a way where we can retrieve it from a single source, there are a lot of open source solutions where, for example, all of these different sharded Prometheuses can ultimately dump their long-term store to something like S3 or GCS. And again, like that is definitely a solution that kind of allows you to pass that initial scaling barrier of a single Prometheus, but at the cost of having this operational complexity. These different Prometheuses aren't necessarily balanced, so provisioning them and maintaining them over time is operationally difficult. And it's also just kind of infrastructurally way more complex, because now you don't just have this one Prometheus instance, you have many, and they're also talking to like these other services that are doing querying and this other, remote storage piece. And so kind of the whole infrastructure has evolved to become a lot more complicated. And then, while those solutions are in place and companies are doing this to handle their kind of surpassed scale, you can even kind of reach a place where even something like this just becomes not sustainable, either operationally or just kind of the cost-effective nature of it is not sustainable, because you don't really have something that is linearly scalable in terms of just like raw dollars. So kind of in this third bucket, the question is, all right, trying to maintain this kind of sharded Prometheus infrastructure with these other open source tools that we've kind of pieced together, it's kind of a nightmare. Is there a solution that actually just can, give us some sort of sustainable solution to the indefinite scaling problem? Kind of one other piece to note about kind of a challenge with that type of many different Prometheuses using some remote store and kind of blob storage is the fact that while you can just cheaply indefinitely scale the storage side in something like S3, because you can just pay for more and more of it, you still kind of have this single bottleneck in terms of the execution side when you're doing the reads from this data. Because, for example, if you're storing all of this data all in blob storage, you still need some service to actually index this information and search through it in a way where you can aggregate it all up properly. And that also tends to overwhelm kind of single node solutions. And so you can beef up this, query engine as much as you want, but you still have that kind of limitation of it being a single pipe towards this enormous set of data. So one last problem with metrics monitoring that comes about kind of similarly to the point about limitations with single node execution is reliability. So, in a case where, let's say, you're running a single Prometheus instance, obviously in that world, you're highly susceptible to an outage because if that one single Prometheus instance goes down, then now you have no visibility into your kind of infrastructure. You wouldn't be aware in this example if app C were to go out because your Prometheus instance is out. And this is also like really bad just from a user or engineering standpoint, because if you don't have the visibility into your infrastructure, then you can't actually like diagnose problems and take actions. So kind of one of the pieces of critical infrastructure is the monitoring side. You kind of have to assume that always will be up. And in the world where you're relying on that infrastructure being kind of the single point of failure, that can be problematic. And then lastly, kind of a limitation with this paradigm is the fact that there, like something like Prometheus on its own doesn't have kind of long-term persistent storage built in, and so you need to kind of come up with some other solution to that, or you're also susceptible to losing data permanently if things just kind of crash. So kind of those 2 points in metrics monitoring have been long-standing challenges that many companies have been encountering for a long time, which are scale and reliability. So that kind of leads us to how do we try to approach those challenges with solutions in M3. And so first I'll just briefly talk about what even is M3. So M3 is an open source distributed metrics engine. So kind of the notable difference between the metrics engine of M3 versus many others is its distributed nature. And it is highly compatible with Prometheus. It can kind of be pointed to by Prometheus. So your single Prometheus or many can just direct all of their read and write traffic to M3, and M3 can kind of be the horizontally scalable distributed system solution to the limitations that exist with kind of a single node solution. And so as we see here, kind of the architecture would look something like Prometheus talks to kind of this arbiter in between called the M3 coordinator, and the M3 coordinator is in charge of issuing kind of, or basically forwarding the operations to the actual distributed system, which is the M3 DB component. And you can see here, this is an example where we have 3 different replicas of M3 DB clusters, which allows us to kind of both have horizontal scaling capability because we can continue to add nodes to each of these replica clusters. And then also because we're replicating the data, if some of these go down, we're resilient to failures. So we'll kind of quickly walk through how those benefits actually play out. So again, kind of on the reliability side, the way we in M3 tackle this problem is via replication. And so, by having this functionality, not only are we resistant to single points of failure, but also just kind of, no downtime requirements for upgrades, no downtime requirements for data migrations, no downtime requirements for kind of deployments and things like that. And you can imagine kind of, let's say all 3 of our replicas are currently working. Obviously, reads are then able to be served in this situation. If one replica goes down, we still can fully serve, consistent reads because we have 2 other copies and have kind of quorum consensus about what the truth actually is. And so only until you actually have 2 replicas down, which would be kind of an unlikely event scenario, would you have, especially if you were to kind of, let's say put one replica in one region, another replica in another, only until you would have two actually down would you no longer be able to provide truly consistent reads. But even then, in kind of this like worst, in this like very bad case scenario, you could still even serve the data that is existing on replica 3 just without kind of the same consistency guarantees that you would have with more than one replica operational. So on the scale side, the way kind of M3 tackles this problem is, again, kind of in its distributed nature. And there are kind of two pieces to this. So again, you can imagine how kind of the database side is actually comprised of many different nodes. And so one really strong benefit of this distributed nature is that you can just add and remove, more nodes as needed, as you need to support greater metrics volume in total. And so it's kind of a horizontally scalable solution as opposed to having to kind of indefinitely beef up a single instance to support more volume. And then kind of the other advantage of this distributed nature is not really related to the storage itself, but rather kind of the read path. And so we talked about earlier how there are limitations with kind of the single node execution path. Well, on the distributed side, when you're doing reads, it actually kind of becomes a map reduce problem where you can kind of distribute that load across all of these nodes in a way that makes it so you don't have that kind of single node execution limitation where that one node needs to be extremely beefy. Instead, we can kind of more evenly distribute this load across kind of much smaller instances that cost less money. And it also just improves kind of, query speeds because we're able to kind of parallelize a lot of the aggregations across the nodes themselves, as opposed to having to happen kind of in some single instance. So those are kind of like the solutions to scale and reliability from the very beginning of M3. And so one could say, oh, okay, well, we must now then have infinitely horizontal scale. So kind of now problem solved, everything is fine. We've removed the blocker that was, the physics limitation of running something on a single instance. So what problems are remaining? Well, essentially the problem then becomes, okay, well, yes, we can in theory just linearly infinitely scale, but you're still linearly paying for that volume as you're increasing the total volume of metric series data you're ingesting. And so in a world where cardinality is certainly not decreasing, so again, kind of cardinality being the like density of all of the different dimensions and how often they're changing, like all of that is not decreasing, and instead in kind of a cloud native world, it's only increasing. So the question is, how do we make sure that while we're scaling these things out, we're doing it in a way that isn't, breaking the bank? And so that kind of leads to the maximization problems that we've more recently been focusing on. And kind of, you can think about these maximization problems as kind of two different buckets. One is just trying to get the absolute most performance you can per dollar of compute spend. But then secondly, and this is a little more kind of like from the perspective of the engineer who's relying on this monitoring infrastructure, what we're trying to maximize is kind of the actual value to that engineer, or the insights one can get from the actual kind of stuff we're ultimately storing. So you can take an approach of let's just store literally everything, and you can do that, but you also are paying for it. So how do we make it so that, for every dollar we're paying to store stuff, we're actually getting the absolute most insight or value to engineer out of that? And so kind of there are a few different problems that we've solved in this space that we can illustrate. So The first maximization problem in this space is kind of the problem of balancing. And this is kind of an inherent problem with the distributed nature of M3. So you could imagine, let's say we have 3 full nodes, right, with 30 days of data. So kind of they have a look back period of 30 days that we're keeping. We're fully at capacity with those 30 days. We want to kind of expand our cluster so that, you know, we can, let's say, add up to 90 days or something. Then we go from kind of 3 to 9 nodes total. So we're going through a migration where we want to add 6 more nodes to our cluster. Obviously, when you first do this, those 6 newest nodes are completely empty. They have no data. What will happen in kind of a world where, you know, we're not taking any action to rebalance in any way, after a single day, our cluster is going to be immensely lopsided because, you know, we'll have the new 6 nodes will have taken writes. And so they'll have now kind of a day's worth of data distributed among them. But then, you know, the original 3 nodes have almost all of the data still. And like, this has many different implications that are negative. So for one, the query load is immensely kind of imbalanced in a way that would result in slower speeds, because you can imagine searching through all of the data on these like really large, on these instances with way more data, it's going to be much slower than if that were actually like evenly distributed among all 9 different nodes. Another problem is that this is just very, you know, operationally cumbersome, because you have these nodes that are kind of changing over long periods of time in how much data they actually will have, right? So kind of at first, 3 of these nodes are huge and full, but then over time that will go down, or over 30 days in this example. And so having to maintain and efficiently only kind of provision instances to what you actually need in terms of, you know, total storage space is much more difficult to manage over time. And then lastly, it's just very inefficient, because like you could, to make things operationally easier, you could still just provision everything to the max point at which you need to support. But the downside there is then now you're, for like a whole 30-day period, you're actually kind of wasting money on servers that have, you know, only a fraction of the data that they're provisioned to hold. So kind of a solution to this is kind of an idea or a piece of functionality called peer streaming. And so the idea here is that whenever we add or remove a node to an M3DB cluster, in the background, the nodes will kind of collectively reassign what data belongs on what nodes, and then they stream data in a way to kind of perfectly rebalance it across the new kind of topology of the cluster. And so obviously the benefits of this are that, you know, when we're provisioning or adding these new nodes, right at the outset, we can provision them to have the correct, efficient amount of necessary resources. And then also right at the outset of kind of doing this addition, as soon as like the streaming has completed, now the query load is immediately even, whereas before it would be kind of a 30-day period where it's very lopsided. So kind of to walk through this example again of adding 6 nodes to a cluster. Let's say, or let's kind of walk through what the steps in this case would be. So, you know, we've added these new nodes, they're empty, then collectively what they decide is, okay, we're going to assign some of these existing shards on the leftmost, you know, 3 nodes to some subset of the rightmost ones. So kind of there's this background assignment of shards going on. Then kind of the second and third steps are actually, you know, streaming that data in the background from the existing nodes to the new nodes. And then as soon as the new nodes have a given new shard fully, on their side, they then kind of publicly say, hey, I have this shard now available. And then that leads to kind of the final step, which is to say, once shards are publicly said to be made available by their new destination, then finally the existing nodes can fully drop that data and then be kind of rebalanced back to what their peers would have. And so kind of the advantage here clearly is now, instead of having to provision these nodes at a point that's like much higher to kind of the max point that they could be, we could just provision them at the outset to have been, what the expected rebalance would look like. And then, additionally to kind of the provisioning benefit, we also now have kind of even query load distributed in parallel across all of these nodes, rather than having kind of some nodes incur much more of a given query cost than others. And just to kind of compare that benefit to kind of some alternative, monitoring solution strategies, imagine how, with a solution that is putting all of the data into some long-term kind of cloud storage like S3 or GCS, while that kind of does have this indefinite scale still, again, you have this kind of single node execution issue where when you're executing a query across all of that data, here's a case where it actually is executing all of the data on this single node, whereas in kind of the peer stream distributed case, all of that's being equally distributed across 9 different instances. Cool. So now let's talk about query load. So another maximization problem is trying to make sure that when we're provisioning instances, we're doing so efficiently. And so here's a graph of kind of query load over a couple of weeks. And this kind of shows how, while query load tends to be generally consistent, it also is kind of unpredictably spiky in many different cases. And so then the question is, like, given that kind of pattern of usage, how do we make sure that our nodes are provisioned in a way that is resistant to out of memory issues and will be able to handle the cases where there's way more load than the norm? So the way we've sought to tackle this in M3 is by providing kind of ability to avoid having to provision query resources to handle worst case scenarios, and to achieve that, we kind of offer controls to tune clusters so that they're protected against those worst case scenarios, as well as automatic transparency into this usage so that engineers who are tuning these clusters can do so effectively. So one limit that it can be put in place to kind of allow nodes to be protected against these, like, this spiky behavior, is being able to kind of put a cap on the concurrent memory that would be resulting from all queries running in a given period of time on a node. So in M3DB nodes, we automatically emit a metric that allows us to get a sense of what that kind of peak concurrent memory usage is over time. So you can then kind of very easily go look at your historical use in these nodes and then use that to inform kind of limits that you set. So you can just put that, right at what is the reasonable median normal query load that you expect to support, and then have that be the cap, so that if in the case where that spikes way above what we've provisioned for, the nodes will actually just kind of either abandon queries or return kind of partial results for queries to make sure that we're remaining under this memory limit. And so you can see here, all of this can be done via configs that are referenced in the M3DB docs. And so here you actually just specify kind of the number of blocks, which is kind of like a consistent amount of memory that would be pulled into memory. And you can specify kind of how many of those blocks you want to allow to be pulled into memory concurrently as a result of queries in some given look back period. And in this case, it would be like within a 5-second kind of look back. And then on top of being able to kind of limit kind of the memory being pulled in across all queries in a given time period, we also emit metrics for single query memory costs and allow people to set limits based on that as well. And that's very useful because it allows you to kind of ensure that there aren't, single culprit queries taking down different database nodes, and you're not having to cater towards those one-off, unique kind of uniquely costly query instances. So in the same way with the global side, we have metrics that inform this. We also then, from the config side, allow people to set these types of caps. And in this case, you can actually set it so that it's either on series and or on docs or blocks as kind of the tracking of memory. And then you can also optionally set here if you want queries to fail in cases where they're exceeding a memory limit, or just kind of truncate the result. So it still returns you results, but just only a portion of them. And so then lastly, a maximization problem is kind of handling the ever increasing write load that we see with, the increasing cardinality of metrics over time. So obviously, if linearly we're seeing just increases in the number of series being produced, we could just linearly pay more to support that. But then the question is, how do we make sure that what we're paying for actually is getting the most engineering value? And the way we can do this is via this kind of other component that can sit alongside the coordinator, and that's called the M3 aggregator. And so what this service does is it allows us to be optionally more selective about the metrics and dimensions we actually care about, so that we're not needlessly storing things that we never actually will look at and get engineering value for. And so the kind of the functionality it actually achieves is being able to kind of re-aggregate metrics by different dimensions to produce different metrics at different types of kind of resolutions and retentions. And we'll kind of walk through what that looks like. So if we kind of think back to our HTTP request latency example, let's imagine how many series would comprise this with, a real life example. So if we were tracking HTTP request latency, so in this case, we're not actually just tracking the count of requests. In this case, we're actually bucketing the time that request took into many different histogram buckets. So here we would actually have, a dimension called bucket, and that, let's say we have 30 different buckets that make up that histogram. Then let's say we have 10 different status codes, 50 different routes, 4 active versions, 4 regions, and then, again, this kind of pod dimension, which are kind of ephemeral pod names that are changing over time, of 100. So if you kind of multiply all those together, this metric would be comprised of actually 24 million series under the hood. If though, let's say we just drop that single pod dimension, and, in this case, we don't actually care about the pods, because when we're thinking about HTTP request latency, we're really thinking about it from kind of a service level or kind of a region level. We're never thinking about it as like a single pod versus another pod that's running the same service. So if you were to just not store the series associated with having to break out by pods, that actually reduces, in this case, the total number of series down by a factor of 100, and that would only be 240,000 series. So if we could actually be able to do this, we can way more efficiently choose what we're storing, but get the same kind of engineering value for it. So this is also to kind of illustrate why it's valid for us to be able to just not care about something like pod. So imagine our M3 coordinator read service. So this is the same service running in the same area, right? But just over time, every time we redeploy it, it's actually being tracked as a new metric, right? Or not a new metric, but like the same metric is being tracked as kind of a new underlying series, which is kind of illustrated by the fact that each of these colored lines is a distinct series. So when we're actually querying this latency, we don't care that our redeployment happened these like 5 different times throughout this period. We're actually going to just aggregate that together, and the dimensionality of pod is just going to be kind of lost. But so from like the user side, we don't care that this had happened. And when we query it, it'll actually look like this, because we're going to query the latency metric. We're going to actually view it from the perspective of just the coordinator, not the coordinator that was deployed at time A versus the coordinator that was deployed at time B, et cetera. So if we're doing this aggregation at query time and we don't care about this dimensionality otherwise, then why are we storing it in that way? Because kind of when you look at what the metrics look like, just broken out by all of the different pods, that would happen over kind of like a, let's say 90-day period where you're doing deployments often, you're incurring this needless like multiplicative series storage for something that you don't even look at. And so it's very inefficient. So kind of to solve this problem, what you can add with the aggregator are rule up rules. And essentially what you can do is you can say, okay, I'm going to kind of sum up all of these, or sum up a particular metrics values by the dimensions I actually care about, but exclude, some other dimension or some set of dimensions. And so in this case, we're saying group by all of the dimensions except for pod. And so what that ultimately looks like is, now on disk, it's actually a single series instead of, what this would look like. And so this is kind of a before after picture of what that kind of collapsing of your collapsing of your metric down by a particular dimension would look like, where you have many different series broken out by pod name, and then we've collapsed them into a single one. And then very lastly, kind of another value of the aggregation side is it allows you to choose how long we keep data around for and at what level of granularity. And what this allows us to be more selective about is to be able to say, hey, okay, maybe I care about, the most raw level of granularity possible for kind of the last week or last month, because diagnosing and debugging issues, for that purpose, it's important that I have like the very most raw level of granularity possible. But let's say I also really do care about kind of year-long trends or month-long trends, but almost never would I need to be breaking out by kind of the same level of granularity, a year ago. So what you can do at the aggregation side is you can say, okay, we want to use this level of resolution, so time resolution, so kind of like the granularity with respect to how often you're measuring something for kind of this period of look back time, but then have this different aggregation that uses a different combination of resolution and retention. And what that allows you to do is say, okay, I want to take and save stuff really granularly for short periods of time and not so granularly for long periods of time. And as a result, it means that we're kind of storing only what we actually will be looking at and not needlessly storing just everything. So just to quickly summarize, and we'll get to kind of the Q&A in a sec. The 3 kind of maximization problem solutions we reviewed here are peer streaming. And so that's rebalancing the different nodes so that load and storage is evenly distributed across them. Query limits and metrics, which allows us to, provision our nodes for the normal load case and not the worst node case. And then lastly, aggregator rollups, which allows us to be way more efficient in choosing what series actually are stored versus, and you know, informing that decision really based on kind of the engineering value or the engineer value, rather than just de facto storing everything, given that that costs money and we want to make sure that the insights we're paying for, we're getting the most insight per dollar. So thank you for coming. I just want to do a quick shout out before we get to questions to kind of all the M3 contributors. So, you know, the folks at Uber, which is the company at which M3 originated, LinkedIn, Cloudera, many other, you know, great contributors to the M3 open source project. We also have like Slack rooms and office hours that are linked here. So feel free to reach out through any of those media. But awesome, and now we can kind of jump to questions. Okay. I guess, should I do this in order? Maybe I'll just do it in reverse order. Okay. Regarding maximization problem B, can you just scale up query nodes in a couple of seconds? Let's see. Regarding maximization problem B. Sorry, I'm just going to pull up that slide. And I can reshare. I just need to zoom out. Okay. Regarding maximization problem B, can you just scale up query nodes in a couple of seconds? Oh, interestingly. So yeah, so I guess so dynamic scaling of the nodes, I guess the problem with that is it's really hard to do that in kind of a just-in-time fashion, right? So like, yes, you can have elastic scaling to some degree, but that, at least on the M3 side, we don't have that kind of as a first class feature. And I think for most people who are kind of managing their resource allocation within their infrastructure, it's really hard to do this in a way that's like so dynamically elastic, that's, you know, a result of just kind of current user usage. And again, the reason that is because you can see in this case how like unpredictably spiky this is. It's not like we're seeing something trending up and so I have time to actually kind of provision the instance to have more memory. You would really need, in order to support those like huge spikes that come about in an unpredictable fashion, you would really need to provision it ahead of time as opposed to being able to just dynamically do that in advance. I guess there are ways to maybe know that, or maybe like queue things up and redistribute those over time. But as for kind of like dynamic elastic scaling, I think that's a pretty tough kind of solution to the problem of this, like, you know, spiky behavior, as opposed to with the limit case where you're kind of just saying, these are rare cases that we just don't want to be harmed by. And instead we can make sure that the resource spending we're planning for is not kind of needlessly excessive and supporting the uncommon worst case. So when you write in your diagram query to S3 GCS, are you referring to remote write to S3 using Prometheus or other open source systems? So I guess, so in that case, it really is kind of like both. So I think there are many different open source solutions that kind of sit in between Prometheus and some cloud storage as the fundamental solution. So, you know, there are a few different open source projects that whose kind of approach is that, and that is kind of what we're talking about when we're talking about the I can go back to that slide, kind of this single execution limitation, right? Where no matter what service is sitting in front of your big cloud storage, you know, option, that single query instance is going to be having this limitation of being just one instance that needs to incur all of that index cost, rather than it being able to be distributed across many different machines. Let's see. What algorithm is, or that one was new. Maybe I should have done this in order. So you mean when using M3, you should deploy 3 clusters of M3DB. So I guess the way to think about kind of the deployment architecture is it's pretty configurable to kind of what one's use case would be, but in general, kind of a recommended deployment configuration would be that you have kind of 3 different replications or replicas, so that you can have kind of the 2 of 3 quorum consistent read guarantees. And each of these you can think of as kind of a different cluster, and then you can indefinitely add nodes to those clusters. So this is a case where like in each of these like replica clusters, we have 3 nodes in them, but you can add more nodes to them over time. And in this case, it's just 3 and 3 coincidentally, but like you could have, 5 nodes in each of these clusters or more as well, for example. Can you add a node and immediately be available to read, write, or do you have to wait for shards to relocate to use it? Like happens in Kafka. Would be coming in, and until kind of the new shard ownerships are made public, that would remain so. But just kind of as the new nodes are fully claiming those shards, then the reads would be like directed to them instead of the original nodes. What do you mean by scaling the aggregations in the query? Does it happen inside the DB nodes? Or you mean the query nodes is using other query nodes to distribute the query nodes? All right, let me see. I'm going to read that once more. What do you mean by scaling the aggregations in the query? Does it happen inside the DB nodes? Or you mean the query nodes is using other query nodes to distribute the query nodes? I don't know if I totally understand the question, but it sounds kind of, so correct me if I'm wrong, and clarify the question if I'm misunderstanding. But it sounds like you're asking how is it that we distribute kind of the query load across the different nodes? And if that's the question, the way to think about it is kind of like all of the series are ultimately kind of sharded randomly across the different nodes. And so when a query is issued, that query fans out to all of the different nodes. Each node is responsible for matching the relevant series data for that query, and then returning it back up to kind of the query service, who then pulls it all together to return to the user. And so kind of in that way though, like the query nodes themselves, the DB nodes themselves are doing various types of aggregations, but also because all of the data is sharded randomly, like a given query is kind of incurring a cost divided by n different nodes, as opposed to the cost being kind of lopsided on one node versus another or something like that. What algorithm is used to rebalance shards? I mean, how is it done collectively? Well, so kind of there are a few different kind of consensus algorithms. Like that are available. And so I'm pretty sure the consensus algorithm in this case is just Raft, which you can look up. And it's a pretty simple one, which is basically just a way of kind of claiming ownership in a distributed fashion and making sure kind of all of the nodes that comprise the cluster land on the same answer of who owns what shard. And so kind of that process is kind of done, and then where different shards are being claimed by new nodes, then that data is streamed to them, and then only once those shards are then kind of publicly said to have been kind of fully retrieved by this new shard do the original nodes say, okay, now it's safe for me to dump my data. But if it were to like not receive that, then kind of the streaming would be like retried in a different way, and then the shard would be kind of reconsensus distributed to some different node. All right, I think that's the last of the queued up questions.
Yeah, hey Ryan, it's Christy again. Do you want to pull up that last slide of where folks can find out more information or connect with you, just in case there are additional questions? Yeah, awesome. There are some links here for Slack. Again, Ryan, thanks for a great presentation and a lively discussion here. Great to see that. And thank you everyone for attending. A reminder that the recording and the slides will be posted later today to the CNCF webinars page at cncf.io/webinars. We hope to see you at a future CNCF webinar. Have a great day, everyone. Stay safe. Thanks.
Thanks, everyone.